Hello students. Welcome to Chapter 2 of UV Spectroscopy. In this chapter, we will cover selection rules, band structure, instrumentation and spectra, the Beer-Lambert law, and the application of UV spectroscopy. Let's start with selection rules. What are they? Selection rules dictate that not all possible transitions are observed. For an electron to transition, certain quantum mechanical constraints apply. For example, an electron cannot change its spin quantum number during a transition. Forbidden transitions can sometimes be observed due to other factors. Band structure in UV spectroscopy is different from IR or NMR. UV tends to give wide, overlapping bands due to the quantized electronic energy levels. In bulk samples, not all bonds are in the same energy states, affecting the wavelength of transitions. When energy levels are superimposed, any transition has the possibility of being observed. This diagram illustrates how energy levels and transitions are related in UV spectroscopy. The construction of a traditional UV-vis spectrometer is similar to an IR spectrometer, requiring sample handling, irradiation, detection, and output. This schematic shows the components of a modern UV spectrometer. Two sources are required to scan the entire UV-vis band, a deuterium lamp for 200 to 330 nanometers, and a tungsten lamp for 330 to 700 nanometers. The monochromator splits the light, and the detector measures the transmitted light through the sample. Dispersive IR requires time to cover the UV-vis band due to changing wavelengths. The diode array spectrophotometer uses a prism to split the light, allowing simultaneous detection by individual diodes, offering higher resolution. UV spectra are typically recorded in solution phase using cells made of plastic, glass, or quartz. Only quartz is transparent in the full 200 to 700 nanometers range. Concentration is empirically determined. Solvents must be transparent in the observed region. The wavelength where a solvent is no longer transparent is called the cutoff. Common solvents and their cutoffs are listed here. Solvents should preserve the fine structure of spectra. H-bonding complicates vibrational and rotational energy levels. Nonpolar solvents generally provide better spectra. The x-axis of the spectrum is in wavelength, and the y-axis is in absorbance. Spectra are often reported as numerical values of lambda max due to the lack of fine structure. Absorbance is the inverse of transmittance. From an experimental point of view, path length, concentration, and molar absorptivity affect absorbance. These factors are combined into the Beer-Lambert law. The Beer-Lambert law combines path length, concentration, and molar absorptivity. Standard cells are typically 1 cm in length, and concentration is varied depending on the sample. Molar absorptivities can vary by orders of magnitude. UV spectroscopy is rarely used as a primary method for structure determination but is useful in combination with NMR and IR. It can assay various parameters and is commonly used in HPLC as a detection device. Students, now let me explain you about chromophores. Chromophores are functional groups capable of characteristic electronic transitions. These transitions are influenced by the functional group and its environment. Alkanes only possess sigma bonds, and no lone pairs of electrons, leading to high-energy sigma to sigma star transitions in the far UV. This transition can cause cleavage of the sigma bond. Alcohols, ethers, amines, and sulfur compounds exhibit N to sigma star transitions, often shorter wavelengths. This transition occurs from the highest occupied molecular orbital to the lowest unoccupied molecular orbital. Alkenes and alkanes exhibit pi to pi star transitions at 175 and 170 nanometers, respectively. These transitions are lower in energy than sigma to sigma star transitions but are still in the far UV. Carbonyls can undergo N to pi star and pi to pi star transitions. Despite being forbidden by selection rules, these transitions are often observed and studied. Substitution effects are significant in these transitions. Carbonyl oxygen approximates sp rather than sp2. This slide shows the transitions in carbonyl compounds, highlighting the N to pi star and pi to pi star transitions. In our study of general chromophores, we observe that only the weak N to pi transition occurs in the UV spectrum. The energy of this transition can be shifted by attaching substituent groups, known as auxochromes, which can increase the intensity and wavelength of absorption. Common auxochromes include alkyl, hydroxyl, alkoxy, amino groups, and halogens. Substituents can affect chromophores in four ways: bathochromic shift, red shift, moves absorption to longer wavelengths and lower energy; hypsochromic shift, blue shift, moves absorption to shorter wavelengths and higher energy; hyperchromic effect increases intensity, and hyperchromic effect decreases intensity. Conjugation is the most efficient way to induce bathochromic and hyperchromic shifts in unsaturated chromophores. For example, beta-carotene shows significant shifts in its absorption spectrum due to conjugation. Conjugation in alkenes decreases the energy required for electronic excitation. According to molecular orbital theory, two atomic p orbitals combine to form molecular orbitals in ethylene, leading to a lower energy transition. In butadiene, mixing four p orbitals creates four molecular orbitals, resulting in a more symmetrical energy distribution compared to ethylene. This reduces the energy gap for the HOMO to LUMO transition. As we extend conjugation to longer systems, the energy gap continues to decrease, leading to absorption at longer wavelengths. This trend is observed from ethylene to octatetrene. Lone pairs of electrons on atoms like nitrogen, oxygen, and halogens can extend conjugated systems, forming auxochromes. These interactions, though weaker than pi systems, still affect the energy levels. Methyl groups can cause a bathochromic shift through hyperconjugation or sigma bond resonance, even without pi or n electrons. Students, in the next chapter, we will quantify the effects of substituent groups using the Woodward-Fieser rules, applying them to conjugated dienes, conjugated denones, and aromatic systems. Students, hope you learned the basics of UV. See you in next chapter 3. Goodbye.